Hello dear students, this is Devangsha from LG Institute of Engineering and Technology. We are learning subject basic electrical engineering. In our previous lecture, time domain analysis of RL, first order circuit, where we have taken a series combination of R and L, resistance and inductor, and we have applied a DC source. Now the same phenomena we are going to repeat, not for a RL circuit, but this is for a RC circuit. So our today's topic is time domain analysis of first order RC circuit, where you can see here from the circuit diagram where two components are connected in series, resistance and capacitor, and the voltage V is applied, that is a DC voltage source is applied to combination of R and C, right, where in we arrange a switch having two position number 1 and position number 2, right. So you can see here the capacitor is connected in series with the resistance, and combination is connected with the DC supply, where at the instant of closing the switch, so here with the instant of closing the switch, series combination is connected with the DC voltage source, right. So by this way the capacitor is going to be charged. So in our previous session we have discussed, we have an inductor and we have a capacitor, both are related with the time, right. So the process is that once you apply the DC source to inductor and capacitor, they are going to charge, right, and once you remove the voltage source, they are going to be discharged. Now during this process is not an instantaneous process, but the charging of capacitor or a charging of inductor is a gradual process, right. So today's session we are going to learn how we are going to charge the capacitor and how we are going to discharge capacitor. So here our aim is check the behavior, to observe the behavior of charging and discharging of capacitor, right. So here once you apply the V is the applied source, Vc is the voltage drop across capacitor, Vr is the voltage drop across the resistance, I is the charging current, and the charge in a capacitor we define as a Q. So once you have Kirchhoff voltage law in this loop, you can find here total V is equal to IR plus Vc, right. So from this I can write the equation V is equal to R into C into dVc by dt plus Vc. Now where I have taken I is nothing but dq by dt. So charge Q, that is equal to C into V, right, and that is nothing but the voltage drop across the capacitor. So current I is equal to dVc by dt. So that particular equation, or that particular term, if I'm going to write, if I'm going to put this term in a equation number 1, I can find V is equal to RC dVc by dt plus Vc. Now I'm just rearranging the particular equation and going forward with some mathematical formula, where you will find here V minus Vc is equal to RC dVc by dt. Again I'm rearranging in this term, so you'll find V dVc divided by V minus Vc is equal to 1 by RC into dt, right. Now in this particular equation, if I am going to multiply by minus 1 both the sides and taking the integration, you will find the integration of minus dVc divided by V minus Vc is equal to integration of minus 1 by RC into dt, right. Once I solve this integration, then I'll find log V minus Vc base of E, that is equal to minus T divided by RC plus K, where I find K is nothing but the integration constant. So my first job is to find the K. Then now this K will represent the initial condition when switch is connected to position 1. When switch is connected to position 1, the current would be flowing through the capacitor. This condition is the initial condition. So at initial condition, always time t must be equal to 0. So if I say the initial condition, when I take the time t is equal to 0, the voltage across capacitor must be 0, right. So this particular term I am going to put in equation number 2. You will find the value of K is nothing but the log V base of E, right. Now once we use these two terms, the value of K, and you put in an overall equation 2, so then you will find log V minus Vc base of E is equal to minus T by RC plus log V base of E, right. So if I'm going to put log another side that term, then I'll find the final equation in this term, like log base of E, V minus Vc divided by V is equal to minus T by Rc, right? Now, my job is to find the voltage drop across capacitor, right, throughout this mathematical analysis. So, if I'm going to convert this particular equation in terms of the Vc, so I'll finally got Vc is equal to V in bracket 1 minus e raised to minus t by rc. Now this is the very important equation where you can see itself in equation there is exponential term, right? So once you find the voltage drop across capacitor with respect to time and you plot on a graph, you can see this kind of graph is available where with respect to time the charging voltage across the capacitor that shows the exponential shape and that represent the term V in bracket 1 minus e raised to minus t by rc, where rc I define as the time constant. Right now, let's analyze this important equation in terms of the graph. So you can find this terminology where I can take the different value of time. Let's say if I'm going to take time t is equal to 0, in this case the voltage drop across the capacitor is equal to 0, right? So that you can put it in this graph. Same way, if you take t is equal to rc, is nothing but the multiplication of values of resistor and capacitor. In that case, uh, you'll find Vc is equal to V in bracket 1 minus e raised to minus 1. Once you take the typical value of E and you will find the equation, you will find the voltage across capacitor Vc is equal to 0.632 into V. So what does it mean? If I am going to take time t is equal to Rc, that means the voltage drop across capacitor or capacitor is charging is 63.2% of total applied voltage. Now that's why I consider RC is nothing but the time constant. Now how, in what sense or how can you assume what is the T in your circuit? So T is nothing but the position of the switch. When switch S is connected to position 1, that is represented by T, right? So what does it mean? If I'm going to connect switch S to position number 1 is equal to the multiplication of values of R and C at that particular moment. If I find the charging across the capacitor, that nothing but 63.2% of total applied voltage, right? So again we have discussed about the time constant. When I take T is much greater than RC, in this condition capacitor will be fully charged, right? So why this is very important, because here you will find the conditions between the closing of the switch and the multiplication of values of R and C. So once you have total two parameters, so based on this total two parameter you will find total three conditions. So condition number 1, when T is less than RC, what happens? See, the T is less than RC, obviously capacitor is undercharging, so capacitor starts charging. One is the position of switch is the time t is equal to rc. In this particular time, we just gone through the equation and that values, you will find the capacitor is charged up to 63.2% of total applied voltage, right? But in which moment charge the capacitor, you must have to take t which is much greater than rc, right? So the time duration of the switch S to position 1 is much higher than the multiplication of the values of R and C, right? You can straight away you can see here, this is the graph of voltage versus the time, where you will find the exponential shape as Vc is equal to V in bracket 1 minus e raised to minus t by Rc, right? Once you are taking a t is equal to Rc, you will see that value is 0.632 into V, right? And as go on, if you can see here, t is much greater than Rc, then this condition is fully charged condition or saturation condition. So as a point of the designer, as a circuit designer, you have to think about the different three conditions, and as per the different three conditions, you can design your circuit. You can design this series RC circuit under DC excitation. Now other way around, let's say if I keep the position of switch S to number 2, where position of switch S or S is connected to position number 2, where capacitor is going to be discharged. So this decay condition you can see here, where switch S is connected to position 2, where everything is same, but in this case you can see the applied voltage battery V is removed from the circuit, right? So my effective circuit is only the series combination of R and C, where now capacitor would act as a voltage source and it starts discharging. So that particular voltage drop across capacitor I want to find, right? So my next job is to find the voltage drop across capacitor, or what should be the discharging voltage across capacitor in this particular circuit. So you can see here, now there is no application of voltage V, so I make it voltage V is 0 by applying the KVL in the particular loop. So you will find here 0 is equal to Vc plus I into R, where obviously I is equal to dq by dt, so C into dVc by dt. You put this term in this equation, 0 is equal to Vc plus Rc dVc by dt. Right, now rearranging this equation, dVc divided by Vc is equal to minus dt divided by Rc. Right, again once you take both the sides, multiplication by minus sign and taking the integration, you will find log Vc is equal to minus 1 by Rc plus K1, right? So you can refer our previous slides and you can also apply the integration. Now from this my job is to find the integration constant K1. So this condition is defined as the initial condition where t is equal to 0. Now the capacitor across voltage, or capacitor is fully charged. So capacitor is having the total application of voltage is V, right? So at initial condition when t is equal to 0, when capacitor is discharging, right, the voltage across capacitor is V. Now this particular value if I'm going to take, so my K1 my K1 is equal to log V. So this particular term I'm going to put it in now in main equation. So you will find log Vc is equal to minus 1 by Rc into T plus log V. Now taking the mathematical term, you can see here Vc divided by V is equal to raised to minus T by Rc. And finally the discharging voltage equation, Vc is equal to V into E raised to minus T by Rc. Right, by this way you can also find, or you can also derive the voltage across capacitor when capacitor is discharging. Now let's say if I'm taking the T is equal to Rc, this time constant, then you will find Vc is equal to V into E raised to minus Rc by Rc. By taking all the values, you can see here the value of Vc 0.368 into V. So if time constant T is equal to the actual position of the switch or time duration of the switch S2, position number 2, that means here the discharging through capacitor, the amount of discharge voltage across the capacitor is 36.8% of the charge value of capacitor. So that value, or that graph you can see here, that under exponential graph, the decaying graph, you can see Vc is equal to V into E raised to minus T by Rc, where if you take T is equal to Rc, that value reaches to 0.368 into V, right? Now here, throughout this RC topic, we learn about the charging and discharging of capacitor. Thank you very much, dear students. If you have any doubt, you can write in a comment box. Thank you very much.